Alright, so in this video we have a blacksmith that drops a piece of iron into a bucket of water that also contains some ice. So assuming no energy loss to the environment, we want to know what the new thermal equilibrium temperature of the system is. Now, assuming no energy loss to the environment tells us that we're doing a calorimetry problem, so that we're going to sum all of our heat values and set them equal to 0, because no energy is going to be leaving or entering our system. And we want to know what the new thermal equilibrium temperature of the system is. So we're going to be solving for TF and assume all items in the system have the exact same temperature. Alright, so there is a hidden Q value in here because common sense should tell you that as soon as you hit a piece of ice with something that's 450 degrees Celsius, that the ice is going to start to melt. So there are going to be some extra Q values or heat values where the ice is going to absorb a certain amount of energy based upon needing to change phase and then raising temperature as a melted substance that we refer to as water. Alright, so what I have here is the energy lost by the iron due to its change in temperature from its initial value down to the thermal equilibrium temperature. I have the heat value for phase changing the ice from solid ice to liquid, which we refer to as water. And then that melted ice, now in water, we have its change in temperature from being at 0 degrees up to what the final temperature of the system is. And then we have the water that was initially at 0 degrees, and we know it's 0 degrees because it's in thermal equilibrium with ice. So the only way you can have ice and water be at thermal equilibrium is they're both at 0 degrees. So I then begin plugging in the values provided. So we have the mass of the iron times the specific heat of the iron, and then we have the final temperature minus the initial temperature. And then the mass of the ice times the latent heat for ice, so the latent heat of fusion to go from a solid to a liquid. And then I have the mass of the ice. Now because the ice melted, you're going to use the specific heat of the water, and then its initial temperature. So remember, phase changes are isothermal, so it's still going to be at 0 degrees. And then the final temperature is going to be that thermal equilibrium temperature. And then we have the mass of the water times the specific heat of water. And remember, it's initially in thermal equilibrium with the ice, so its initial temperature is also 0 down to the final temperature. Now you do have to be careful when working with these. You have to remember to multiply these together and then distribute, which is how I get these first two terms here. Then we multiply this together to get this term here. Then we're going to multiply these two together and distribute. And the nice thing is that when you distribute here, you get 0, so I didn't write that down. And then we multiply these two together with this TF, which should give you this last value here, and then these two multiplied together to distribute it to 0 just gives you 0. You're going to collect all of your terms with the temperature final in them, and then you're going to collect all of your values of energy, and then finally you're going to divide to get your final temperature. And do be careful with these problems. If you get an answer where the final temperature or the thermal equilibrium temperature is outside of the range of the initial temperatures of the items in the system, that should tell you did something wrong, because that tells you you either lost or gained energy. So this value here is in between 450 and 0 degrees. And it's going to be closer to the initial temperature of the ice and water, so your ice bath, because remember, not only did a lot of the energy go into melting the ice cube, but also water has a very high specific heat, so it would have absorbed a lot of the energy from the iron, which has a much lower specific heat, in fact almost by a factor of 10, before reaching a thermal equilibrium temperature.